Hello and welcome to the BioRT-HBV modeling video series on carbonate weathering, where we'll walk through how to set up a carbonate weathering reaction in the BioRT model. And so in this video, I'll go over some background information that will help you understand how we represent chemical weathering reactions in BioRT, and we'll briefly discuss the importance of chemical weathering processes, reaction thermodynamics, transition state theory or TST rate law, and primary and secondary species. So chemical weathering comprises the processes of mineral dissolution and precipitation. And so when we think about chemical weathering within catchment hydrology and biogeochemistry, we think about how it affects the catchment subsurface and water chemistry. So dissolution develops porous space for water storage and flow in the subsurface, while precipitation can clog pore spaces. And so weathering also transforms bedrock into soils, as depicted in the figure on the right. Weathering releases solutes in water and makes essential nutrients available for ecosystem productivity. And so in this video, we're going to focus on carbonate weathering, which is especially important because approximately 7 to 12% of the Earth's land surface is underlain by carbonate geology, and approximately 25% of the global population relies on waters from karst aquifers. So we're going to focus on calcium carbonate weathering, and there are a few different pathways for calcium carbonate weathering as shown here. And so in the BioRT database, the reaction is written as the last pathway shown here, where we have calcium carbonate going to calcium ions and carbonate ions. And so this reaction is what we're going to focus on for the rest of the video. Okay, so to give a quick overview of reaction thermodynamics, an example reaction is written here, where alpha, beta, gamma, and delta are stoichiometric coefficients on reactants A and B and products C and D. So the equilibrium constant, or KEQ value, quantifies the relative amounts of products to reactants at chemical equilibrium, which occurs when the forward and reverse reactions occur at the same rate. And so in this KEQ equation, the letter A represents the activity of constituents, which can be approximated by concentrations in dilute natural waters. And so similarly, we can calculate the ion activity product, or IAP value, which quantifies the relative amounts of products to reactants at any given time, so not necessarily just at equilibrium. And so we can determine if a reaction is at equilibrium by comparing the IAP value to the KEQ value, or by calculating the saturation index, shown here at the bottom. And so when the IAP value is equal to the equilibrium constant, or the SI is equal to 0, the reaction is at equilibrium. When the ion activity product is greater than the equilibrium constant, or the SI is greater than 0, the reaction proceeds to the left. And then lastly, when IAP is less than the KEQ, or the SI is less than 0, the reaction proceeds to the right. And so to put this in context with the calcium carbonate weathering reaction, we can write out the reaction, the KEQ, and IAP expressions here. So we have our products, calcium and carbonate, in the numerators of these expressions, and we have our reactant, solid calcium carbonate, in the denominator. And so the stoichiometric coefficients for each of the constituents is 1, and the activity of a solid is also equal to 1. So we don't need to include the concentration of solid calcium carbonate in either of these expressions. And so the expressions for KEQ and IAP for this reaction are pretty simple, just the concentration of calcium ions multiplied by the concentration of carbonate ions. And so again, we can tell if the reaction is at equilibrium if the IAP and KEQ values are equal. If IAP is greater than KEQ, the reaction proceeds to the left, or through precipitation in this example. And then if IAP is less than KEQ, the reaction proceeds to the right, or by dissolution in this example. And so we can quantify the rates of the reaction using the transition state theory, or TST rate law, which is written here in a simplified form. So each of the K values in this expression are kinetic rate constants. The A values represent the activities of the hydrogen and hydroxyl ions, and N1 and N2 describe the rate dependence on those activities. These values are all given in the BioRT database, which I'll discuss more in the next video. So A is the surface area of the weathering mineral per unit volume of porous media. IAP, again, is the ion activity product, and KEQ is the equilibrium constant. And so the term IAP over KEQ quantifies the distance of the reaction from equilibrium. And so this IAP to KEQ ratio is essentially the driving force of the carbonate weathering reaction. And so the last topic that we need to cover to understand how we set up the carbonate weathering reaction in BioRT is the concept of primary and secondary species. So in general, some reactions can be slow and kinetically controlled, which is the case for a chemical weathering reaction and why we need that TST rate law. And some other reactions can be fast and thermodynamically controlled, where the activities of reaction species are algebraically related through their equilibrium constants or through laws of mass action. And so this is the case for carbonate speciation reactions, where different forms of carbonate, so dissolved carbon dioxide, bicarbonate ions, and carbonate ions, all dominate under different pH conditions, as shown in this figure on the right. So we'll return to this example in a moment. But essentially, primary species are the species that can be used to express all secondary species. And so they're the chemical building blocks of chemical systems. And then secondary species depend on those primary species through laws of mass action. Now, in order to determine the primary and secondary species of a given system, you can take the total number of aqueous species in that system, subtract the number of dependencies or laws of mass action between those species, and that gives you the total number of primary species that you need to define. So let's go through an example. So here we have calcium carbonate in water, and we can start by listing out all of the aqueous species that can form in this system. So in an aqueous system, H2O or water is implied, but we'll list out hydrogen and hydroxide ions explicitly. From the calcium carbonate, we can get all of those carbonate species that I just mentioned, so carbonate ions, bicarbonate ions, and dissolved carbon dioxide, which is equivalent to carbonic acid, or H2CO3. We also have calcium ions and other species that can form amongst these that have already been listed out, like calcium hydroxide, aqueous calcium carbonate, and calcium bicarbonate. And so that gives us 9 species total. We then list out the number of dependencies or laws of mass action with defined equilibrium constants between those species. And so one we can always start with is water forming from hydrogen and hydroxide. We also have equilibrium relationships for each of our carbonate species, which is shown here with bicarbonate and carbonic acid. And we also have laws of mass action for calcium hydroxide, aqueous calcium carbonate, and calcium bicarbonate. So that gives us 6 dependencies or laws of mass action. So subtracting the number of dependencies from the number of species, we get 3 primary species that we need to define. And so to choose which species should be the primary species, we need to consider which species would allow us to form all of the other species in the system. And so we can check this by making a table like the one here on the right, where we have all of the aqueous species in one column here on the left, and then we have 3 potential primary species in these additional columns on the right. And so I've chosen hydrogen ions, calcium ions, and carbonate ions as my potential primary species. And so working through each row in this far left column, we can determine if that species can be formed by the primary species through one of our laws of mass action listed here on the left. So going through these one by one, hydrogen is one of our primary species and so is taken care of already. Hydroxide can be formed from water, or H2O, minus 1 hydrogen ion, as we get from this law of mass action here. Carbonate is, again, a primary species, and so that's covered. Bicarbonate can be formed from 1 hydrogen ion and 1 carbonate ion, shown here in this law of mass action. The carbonic acid can be formed from 2 hydrogen ions and 1 carbonate ion, as shown in this law of mass action. The calcium ion is a primary species, and then calcium hydroxide can be formed from 1 calcium ion and 1 hydroxide ion, which is essentially minus 1 hydrogen ion. And then calcium carbonate can be formed by 1 calcium ion and 1 carbonate ion. And finally, calcium bicarbonate can be formed by one hydrogen ion, one calcium ion, and one carbonate ion. So all of our secondary species here can be formed from these three primary species. Note that these are not the only three primary species that you could have chosen, but this combination is one of the more simple and straightforward options. In addition, certain species are already defined in the BioRT database as primary species, so identifying those will help you choose your primary species and will make setting up the reaction in BioRT easier. So that's all I have for this video. Thank you very much for watching. In the next video, we'll go over the BioRT input files and how to set up a carbonate weathering reaction in BioRT. Thank you.